So today we're going to dive a little bit more into titrations, and specifically we're going to deal with a weak acid being titrated by a strong base. So let's just jump right in. It's incredibly important to know that all titrations take place in two steps. Step number one is we have to do the stoichiometry. Now I always talk about this as taking care of the big dog, and that is whenever we're adding our titrant, whatever's in the burette, down into our Erlenmeyer flask like we watched in the previous video. So whenever we're adding the strong base, in this case, down below, we have to figure out what that has done to our analyte, our weak acid, before we go any farther. So whenever we're dealing with dropping in a big dog or a strong acid or a base into our analyte, we've got to do it in moles. And the way we do that is we use something called an IRT table. It's very similar to an ice table, but what we're doing is we're trying to keep track of the moles of acid or base that we're adding in and know how many moles of the thing that we're titrating has been used up. We can use millimoles. In fact, today during our example, I'm going to use millimoles all the time, and that's essentially moles divided by 1,000, but it allows us to not have to do decimals. And whenever we get done with this first step of do the stoic, or taking care of the big dog, we must then convert back into concentration. And when we do concentration, we've got to account for the fact that we've poured two things together, so our new volume will impact our molarity. The second part of our titrations is always doing an equilibrium problem. Now, we will, whenever we possibly can, use the Henderson-Hasselbalch equation. And you'll see how that applies now. Only when we can't will we use a Rice table. So let me just introduce you to the IRP table. Again, it stands for initial number of moles of each reactant. Now it's the reaction change of the moles. In other words, how many moles have been reacted in both the titrant and the analyte. And then finally, the product moles, because the product moles are what are going to be then used to do the equilibrium problem. The other thing you need to be aware of here, and if you read the side here, it says that whenever we're dealing with an IRP table, that is, in other words, an initial reactant and product, we have to be reacting two things that will react with each other. So like in the example we're going to use OH minus, or NaOH, and HCl. If you have two things that are the same and you're just adding more of one of them, you're not going to use an IRP table. The second table, and this is, I cannot emphasize this enough here, I'm going to star this. Once you've taken care of your IRP table, you're going to get a certain number of moles here and here, right? Those moles must be converted to molarity so that you can then move on and do the Henderson-Hasselbalch equation or Rice. Now, this is the Henderson-Hasselbalch equation. I'm going to refer back to it a number of times as we go through these problems. But the best way to tackle these problems is, of course, by doing these problems. But before I do that, I want you to understand that we're going to be doing titration curves. In other words, drawing a graph of titrations as we're going along through this problem. So there are always 5 places that we want to mark on our graph, and then we'll connect the dots. Initial, pH after adding a small amount, the half equivalence point, and after we've gone past the equivalence point. Again, right now as you're watching this for the first time, it may not make a whole ton of sense. So the best way to do this is to try a problem. So let's do this. Have your calculator out so you can play along at home, but we're going to find the pH when we titrate 0.3 molar HF with 0.3 molar NaOH. And so to point that out for you, what we have is we're going to have up here in our burette, which I cannot draw very straight, in our burette, we're going to have NaOH. And below in our Erlenmeyer flask, we're going to have our HF. So we're going to first drop a certain amount of the NaOH down into this, and then we'll pause, see what it's done to our HF, and then we'll do an equilibrium problem. So as I said, whenever we're doing problems like this, we're always going to first start by figuring out the pH of the acid before we do any adding in of our NaOH. So if you think about it, what do we do always? Well, we take our HF and we throw it into water. This should be familiar to you, and then we're going to do our ice table. Now, I'm not going to make the pretty box that they did, but initially we have, if we take a look up here, 0.3 molar of this. So we're going to write 0.3 molar here, and we have 0 and 0 here. Since this is a one-to-one equation, you guys remember you subtract x here, we're going to add x here and add x here. We're going to look at the fact that the Ka is 6.6 times 10 to the negative 4 and realize that that's not very much. So we're going to be able to 5% rule our x out of this equation. We're going to end up with x and x. A general reminder here, it's always helpful when you're writing this out for a grader that you write what the actual equilibrium expression is, or the law of mass action. I'm going to use those two terms often, so that they know what you're substituting in for. So this is our equation, right? And that's all equal to our 6.6 times 10 to the negative 4. So if they ask us for, again, the law of mass action or the equilibrium expression, this is what we're going to write. When we plug our values in, this is going to have the familiar dead frog look, and it's going to look like this: 0.3 minus x, and we're going to 5% rule. And it is important that you write 5% rule here, and that's going to be equal to 6.6 times 10 to the negative 4. Now, I've gone ahead and done the math here, but if you do, you're going to have to multiply 0.3 by the 6.6 times 10 to the negative 4, and you're going to have to take the square root. But if I take my x value here, it's going to be equal to 0.013745, which is an ugly little number, but that's also equal to our H plus concentration. Now, just a gentle reminder, we want to find the pH at each one of these 5 points here. So we're working on this one right here, and the pH is always the negative log of our H plus concentration, which in this case would be negative log of 0.013745. I'm keeping these numbers in here because I can. The reality is that I will likely, if I wasn't, I would cut it off to maybe 3 significant figures or 2 significant figures, because I know that ultimately, since I use 6.6, my answer can only have 2 significant figures. But when I do this, my pH is going to end up being equal to 1.86, which is a pretty low pH. And I would invite you to look at the graph at the end of this to see how we got this 1.86 in there. Now, we're going to move on. After we've done the 1.86, after we figure out an initial point, we're going to figure out what is the pH after we added 10 milliliters of the 0.3 molar. Now, here's what you have to be aware of here, is that now what we're doing is we're having our HF, and we're adding directly into that, we're adding OH minus. So this is my equation that we're, and you may think, well, what about this Na plus here? We don't care about that. When we react those two together, what you're going to end up with is you're going to end up with water, which we don't really care about, and F minus, which we do care about. So we're going to do initial, react, and final. Okay, now I wanted to talk about how we're going to deal with millimoles, because I don't want to deal with moles here. And so the way this works is pretty straightforward. We have 10 milliliters of 0.3 molar NaOH. Now, 0.3 molar, and if you remember from before, molarity is always equal to moles over volume, right? I can rearrange my molarity if I want to make it to equal to millimoles over milliliters. It's going to have the same value as mole per liter. So what we can do is we can just go 10 milliliters and we can multiply that by my 0.3 millimoles per milliliter. And for my OH minus, which is what we care about here, I'm going to end up with 3 millimoles of OH minus. Similarly, remember we started off with, and I'll scroll back up here for just a second, we started off with 25 milliliters of 0.3 molar HF. So same deal here. If I have 25 milliliters of the, in this case, 0.3 molar per milliliter HF, that's going to give us 7.5 millimoles, and I forgot to put millimoles here, of HF. So when we look at our initial here, we're going to have 7.5 millimoles. And here we're going to have 3 millimoles. And we're going to have none of this and none of this to start off with. So remember, we're just dropping OH into HF. Now what we know is this reacts in a 1-to-1 ratio. So they're going to completely attack each other and use each other up. So this big dog, we're going to use all of it up. So we're going to lose 3 here, and we're going to lose 3 here. Now, because this is a 1-to-1 ratio, what that means also is we're going to gain 3 here, and we're going to gain 3 millimoles here. So what's the net result going to be here? Well, we're going to end up with 4.5 millimoles of this, 0 of this. Now, I should have not even bothered with this because H2O, we don't care about its molarity. But do you see how I'm going to have over here 3 millimoles of my F minus? Now, what that allows us to realize here is that if we do the math, we've taken care and we know that we have, after the big dog has been dropped in, we have 4.5 millimoles of the HF, and we have 3 millimoles of the F minus. But anytime that we are doing a problem, after we've taken care of our IRF table, we've got to convert it back to volume. And so if we take a look at the volume here, we always started off with 25 milliliters of the HF. That's our starting point always. But here, haven't we added in 10 milliliters to it? So if we take a look at our very poorly drawn Erlenmeyer flask, we have 25 milliliters of the HF in here, and to that we have added in an additional 10 milliliters. So what's my new volume? It's 35 milliliters, and that's kind of nice because what I can do here is immediately divide both of these things by 35 milliliters, and what that's going to do is that's going to give me my molarity that I can go into my next step with. So this right here, all of this has been the RIF table step. We're getting ready to do the equilibrium step. Now, if I actually did the math on this and set up the problem, this is going to be equal to 0.1287 molar, not ml, molar, and this is going to be equal to 0.0857 molar. Now, we have right now our HF and F minus. This is essentially a buffer because we have an acid and a conjugate base, which means that we can go up here, and if we take a look at our Henderson-Hasselbalch equation, we can use our pH equals pKa plus the log of AHA, which is the base over the acid. So if I plug that in down here, I'm going to go pH is equal to the pKa of the plus the log of the base over the acid, right? In this case, that would be, I probably should have done F minus and HF. But if I plug my values in here, I'm essentially going to be ending up with pH is equal to the log of, I said, and by log I mean negative log because doesn't P mean negative log, of 6.6 times 10 to the negative 4, all plus the log of these two values plugged in here. So this is going to go into here, this is going to go into here. Again, pardon the messiness with my writing on this. 0.0857 all over 0.1287. When I do the math on this, my pH now is going to be equal to 3.18. And by that, I mean 3.00. Jumped ahead of myself there. So we've gone up significantly, right? We went from a pH of 1.86 here to now a pH of 3.00. Next, we're going to get to a very special place in every equilibrium, and that's where we deal with something called the half equivalence point. So remember, the equation whenever we're dumping big dog in is we're going to take whatever is in our analyte, which is our HF, and we're going to add our big dog to it, and we're going to do it only in moles. So we have to figure out our moles again, and the nice thing is from the previous problem, we already figured out that for our HF, we have 7.5 millimoles. Now, our OH, we now have to do the new millimoles for our NaOH, and again, just a reminder, we don't care about the Na, but if we deal with our 12.5 milliliters of 0.3 millimoles for every 0.1 milliliter, and again, that's the same thing as saying 0.3 whatever, 0.3 divided by 0.1, we're going to get 3.75 millimoles of our OH minus. So this is our H plus, This is our OH minus, and we're going to plug them into our ice problem. Gentle reminder again that when we do our ice, not our ice problem, our IRF problem, when we do that, we're going to end up with F minus, and we're going to end up with H2O. I flipped them over because it makes it a little bit easier to see them closer to each other. So I'm going to start off with 7.5 moles of this, and I keep on saying moles, but I really mean millimoles, because it's been hard to draw with this. And I'm going to have 3.75 millimoles of this. Now, we start off with 0 of this, and we don't care about the water. Since it's a 1-to-1 ratio, and the big dog will always chomp into this HF, what we're going to be left with on this side here is 3.75 being subtracted from both of these totals and being added over here. Because remember, it's a 1-to-1-to-1 ratio. So what's my net result here? I'm going to end up with 3.75 millimoles of HF, none of this, and 3.75 millimoles of my F minus. This is incredibly cool because we have exactly the same quantity of both. Now, we always have to convert to molarity, and now what we've done is, remember, every single time inside of our flask we have 25 milliliters, and by that I mean 25 milliliters of our original HF, and now we're adding in 12.50. So in both these cases right now, I'm going to want to divide by 37.5 and 37.5. And if you're good with math or just shifting decimal around, wouldn't that give us 0.1 molar of this and 0.1 molar of this? Now, I said it was the half equivalence point because if you take a look, we used up exactly half of my HF. So I started with 7.5 millimoles. Now I have 3.75 millimoles. Therefore, I've used up half of my original. So when we plug it into our Henderson-Hasselbalch equation, pH equals pKa plus the log of our F minus concentration all over our HF concentration. I don't know if you guys, how familiar you are with the math of logarithms, but if I have the same number on the top and the same number on the bottom, that's the same thing as taking the log of 1, which is equal to can make your pH equal to pKa. Now, we still have to take our negative log of our Ka, but in this case, if we do pH is equal to pKa, that's going to be equal to the negative log of our Ka, which happens to be 6.6 times 10 to the negative 4, and now our pH is equal to 3.18. So we only went up slightly, and that kind of makes sense because we have a perfect buffer here. So our third point is going to be at the equivalence point. And I'm going to go through this a little bit more quickly, and you can see the steps of how we figured out the millimoles afterwards. But this is our IRF. We're going to add in our OH minus into this, and we're going to end up with F minus and H2O. Now, initial, what reacted, and our final. Here we have our original 7.5 millimoles, but now when we add in 25 milliliters of this, it is equal to 7.5 millimoles of our OH minus. So I have 7.5 millimoles of my HF, and I have 7.5 millimoles of my OH minus. Again, we have 0 and 0 of these two things. But since it's a 1-to-1 ratio, we're going to go minus 7.5 here, minus 7.5 here, and you got it. We're going to have 0 of our original, 0 of this, and all of my HF has now been converted over to F minus. Now, this is a big deal because the point at which we use up exactly the HF that we've started with, we call this the equivalence point. In essence, what we've done is we have caused the HF to completely get used up. And this is where we typically see the color change when we put a titration, an indicator into our solution. But the other thing you need to be aware of now is that the only thing that's left over is F minus, and that causes us to have to do a problem that's a little more difficult. Because in the past, we were able to use our Henderson-Hasselbalch equation, right? Our pH is equal to pKa plus the log of the base over the acid. But here's the thing. We don't have any acid here. So we can no longer use this problem. So what do? Well, now we're stuck with an equilibrium problem, and it is an ice problem that we're going to do. We're going to take our F minus and we're going to throw it into water. F minus, and we're going to throw it into water. And this is what happens at every equivalence. And we're at an equilibrium, and that's going to form HF plus OH minus. Now, here's where we absolutely have to divide by the new volume. Now, we've added 25 milliliters to the 25 milliliters that we originally had in our container. So we're going to have to divide this by 50 milliliters. And 7.5 millimoles divided by 50 milliliters is going to give us 0.15 molar. So my ice problem here, this is going to be 0.15 molar. Now, we're doing a straight ice problem, so we're starting with 0 of this and 0 of this. Our change is going to be minus x, and it's going to be, again, plus x plus x. We've done this before. And we're going to have 0.15 molar minus x, and then we're going to have x over here and x over here. Now, what you need to be aware of, though, is we're going to do now a Kb, because this is the conjugate base of the original. Now, just a general reminder that when we talked about this before, I'm going to erase this because we don't have a ton of, it's kind of clogging in here. Remember that we said that the Ka was equal to the Kw was equal to Ka times Kb was equal to our Kw, and our Kw is equal to 1.0 times 10 to the negative 14. Well, we know that our Kb in this case is 6.6 times 10 to the negative 4. So can't we solve, therefore, for Kb by dividing the 6.6 times 10 to the negative 4 into the 1.1 times 10 to the negative, or 1.0 times 10 to the negative 14? And when we do that, we get a Kb of 1.515 times 10 to the negative 11. Now that is important because when we do our Kb expression now, our Kb is going to be, and this is our law of mass action, right? It's going to be equal to HF concentration all over all multiplied by our OH minus concentration all over our F minus. And that's going to be equal to 1.5, let's call it 1.52 times 10 to the negative 11. When we plug our values in here and we do our x, and again, this is almost rote, and you might be tempted to skip these steps, and I wouldn't blame you, but a grader might want to see it. 0.15 molar minus x. We're going to 5% rule this. My pen is getting a little jumpy here. And that's all going to be equal to 1.52 times 10 to the negative 11. When we do that and we solve for x, our new x value ends up being 1.508. Now, what's important to remember is that this 8x is equal to my OH minus concentration. And remember, we're trying to figure out our POH. So you can do this one of two ways. You can get the POH by taking the negative log of your OH minus concentration. And that's what I'm going to do. Or you could take your OH minus concentration and divide it into our 1.0 times 10 to the negative 14. But either way, when we do our POH and we take the negative log of 1.508, what we end up with is a POH of 5.82. Now, in order to get our pH, we go 14 subtract 5.82, and that's going to give us our pH, which in this case happens to be 8.18. Now, I want you to notice something here. Our pH at the equivalence point is above 7. And that's because at the equivalence point, the only thing we have in the water is a base, F minus. So the result is anytime you start with an acid that you're titrating, at the equivalence point, there's going to be no more acid, only the conjugate base, and that conjugate base is going to make the solution slightly basic, and that's going to give your pH slightly above 7, which in this case is 8.18. So this is the hardest math to do, is when you're at the equivalence point. The next easiest one to do is when we're past the equivalence point. And if you note right here, all we did is we decided to add in just a little bit more than the 25 milliliters, which was the 7.5. And when we do that, we end up with 7.8 millimoles of OH minus. Now, here's what we can do. And we love this place because when we add in the OH minus to our HF, we're going to end up with F minus and again water. And incidentally, in case you're wondering here, we always start from scratch. Whenever we're adding in this 7.8 millimoles, we're adding it into the original 7.5 millimoles that we start off with. So we have 7.5 millimoles of this, and now we have 7.5 millimoles of this, 0 and 0 of this. Now, because you're good with math, you're going to realize, and I said 7.5, what I really meant is 7.8. So my 7.8, now the limiting thing is 7.5. So I'm going to lose 7.5 here, and I'm going to lose 7.5 here, and I'm going to gain 7.5 here. The net result is I have 0 of this, I have 0.3 millimoles of pure OH minus, and I have 7.5 millimoles of my F minus. Now what that means is in my container, I have pure OH minus, and I have F minus, and I have water. Now, this pure OH minus is big dog. So yes, the F minus can dissociate, and we talked about this in the previous problem where we had our F minus get thrown into water right here, and it formed a certain amount of OH minus. But whenever you overrun your buffer, and here's where the big dog, the NaOH or the OH, has overrun our buffer, this 0.3 moles or millimoles, that's going to determine our pH by itself. So if I have 0.3 millimoles of this left over, I can divide it by my new volume. And again, remember, we had 25 milliliters of our HF, and to that, our HF, and to that we're now adding 26 milliliters of our OH minus. Wouldn't that leave us with, 51 milliliters of the solution? So if I take my 0.3 millimoles of my big dog OH minus, this is my concentration that I'm now figuring out of my OH minus, and I divide that by 51 milliliters, I'm going to end up with a concentration of 0.00588 milliliters. That's pure OH minus. Well, how do we figure out the pH of pure OH minus? Well, we figure out our pOH first, which is the negative log of this 0.00588. By the way, you could also write this as 5.88 times 10 to the negative 3. That works out just fine. And when we do that, we end up with a pOH equal to 2.23. Just a reminder, remember, pH plus pOH equals 14. So wouldn't I take my 14 and subtract 2.23 to get to my pH? And when I do that, my new pH is equal to 11.77. Now we could add in more points. We could add in more than 26 milliliters, and the pH will increase slightly, but essentially we've done our job. We've shown the overall curve, and I want to show you how this curve looks. So take a look at this and realize that we're going to do a bunch of these. So if any of this wasn't clear, kind of highlight that in the video, and then we'll talk about it in class. Okay, so when you look at this graph, we've put pH on the y-axis, and we've put the amount of NaOH in milliliters on the x-axis, and we're just going to plot the points that we got from our weak acid being titrated, our HF, and the first place we have here is a pH of 1.86, and that's when we've added nothing. That's if when the acid is by itself, it's 1.86. Now, the second was occurred at 10 milliliters, and we have a pH of 3, so that's going to put us right here. Third is at 12.5, which is just halfway through here, and it's only gone up to about 3.18. And then our equivalence point, which is at 25 milliliters, it is at 8.18. So we're going to go all the way up here to 8.18, which is right about here. And then after we put in too much at 26, which is just a scotch over this, we're up here at 11.77 or so, about right here. Now, one of the things you have to be aware of when you're doing these titration graphs is that they aren't connect the dots. You're not going like this. What actually happens is you immediately have the pH shoot up and then it evens out. And it keeps on evening out until it gets close to the equivalence point, and then it shoots up. Now this point right here, that's our equivalence point. And that's where we've literally have gotten rid of all of the original HF that we had. But then it keeps on shooting up until it hits a point where it kind of levels back off at the end. So we could keep on adding as much as we wanted to, and the pH isn't going to go up a whole bunch. And this is admittedly a pretty rough drawing here, but the 2 points we really care about are this point right here and this point right here. This is the half equivalence point. And the half equivalence point, if you note here, oops, that's not the half equivalence point. This is the half equivalence point. This is the point we really care about, this one right here. And that right there, the half equivalence point, that's exactly where we've used up half of the acid. And there's another truth here that the pH is equal to the pKa. And that in itself is an argument. So you could say the half equivalence point, we're at the half equivalence point, therefore the pH is equal to the pKa. But notice that this is at 12.5 milliliters, right? It's exactly half of the equivalence point. So you can, if you ever know where your equivalence point is, you automatically are going to know what your half equivalence point, and you're going to know that your pH is equal to pKa. So hopefully this has been helpful to you. We're going to practice a ton on these, and I'm going to get better at drawing graphs like this.